Uh, I think I've got it right. Hello, everyone. I'm hoping you can hear me. Yeah, my name's Didam Turelli. I'm the person who is responsible for this course on the mechatronics side, and I'll be lecturing to you for the next 3 weeks. Yeah, hi. I'm actually currently chair of mechatronic engineering, but I'm actually an electrical engineer. In fact, hello. In fact, I'm in the communications area. Signal processing and communications is my area, which may seem strange because mechatronics has to do with machines, and communication seems more electronics, right? But what I noticed is it's partly chance because there's nobody else here, but also partly because when you look at the mechatronics department, the last 3 or 4 people who were here, who were here were indeed signal processing people, because there is so much communications and signal processing. For instance, we had a mechanical engineer, and I'm thinking of Ika and Tolga Hoca. Ika Hoca and Tolga Hoca have left right now, but one of them is at Yıldız Technical University. The other one is working for a company, an automotive company, but they were mechanical engineers, but their PhD was on GPS signals. So their PhD topic was actually in communications, even though they were mechanical engineers. And I'm going to talk a little bit about that, about why we're studying communications and electronics even if you want to do something very different from there, because it's kind of like the world is changing right now. We have to know about computers. Even if you're a mechanical engineer, you have to know some computing, right? And you have to know a little bit about communications. I actually prepared a presentation, amazingly, which I'm not very good at. Let me do the screen sharing. Okay, I only have one monitor. I'm trying to fix the situation, but currently I only have one monitor. So hopefully you guys, and this is a hodgepodge of different different slides, because I've got some of my own slides, but I couldn't find my own slides. So whatever I wanted to put on the slide, I Googled. So I ended up using, these are my sources for now. And also there's other sources, like some of them are from my own slides and so on. Okay, so we'll talk about this stuff. So next 3 weeks, I will cover some communications, maybe a little bit about embedded systems. I'm not sure if we'll do that, and a little bit about electronics. Okay, so what you'll see in future classes. Okay, so this is the communications timeline of modern communications here. I'll make this bigger. You guys should learn PowerPoint. It's a good thing to learn. Anyway, so if you look at it, really communications really started with in 1876, first telephone call, right? 1920, the 20s, you have the radio broadcasts, and of course the TV broadcasts start around 1936 with the infamous Olympic Games in Berlin. And then you have 60s and digital communication comes around. 65 is the first commercial satellite. And then the 70s, they start inventing the internet, right? The internet starts off as a project from the United States. They have a defense agency, DARPA, Defense Research Agency. I forget what it's short for. But they start thinking how we should connect computers together, which seems a very weird idea, considering, before that, I don't know if it's even pre-fax, but even with a fax and telephone, you just have site-to-site links, single links. But here, they were trying to kind of make a mesh where you could send something to multiple people. And they were talking about sending data at a time when no one was sending data, right, in 1970s. In 1980s, TCP/IP algorithm was developed. And 1993, so after this, in the 1980s, I remember being young, and my aunt was working at IBM in Turkey. And she told me, oh, we have this system, and you can ask for IBM in Italy to send you a book, and they will download it overnight, and then we print out the book, and you have the book. And I just remember being so amazed by that you could send this data so quickly, because it was so hard to access books that were outside the country, make phone calls from outside the country. All of these things were very, very difficult. Okay, you guys are still here, right? Sorry. Just checking. Let me go back to, okay. So all of these things were very difficult, and they became really a thing with the internet, right? I'm just going to keep this side open because then I can see if you write anything. Okay, so this is kind of the very brief history of internet. 1993 was the invention of the web. I was in college at the time. That's how old I am. I was in university. And I remember in 1992 or 93, we had this program called Chat. What was it called? It was called Talk. And if you went to a Linux terminal and you typed Talk, because it was all like Windows was out, but not everyone had Windows. You would type Talk, and then it would connect you to a random person. And again, like this was very, very revolutionary for the time. So yeah, so the things that you take for granted today, just being able to call anyone in any country, being able to send documents, you know, these things are actually very new, and they've really changed the way that we do things in business, at schools, everywhere. And you know, that makes me wonder, you know, 20 years from now, when you become engineers, when you're practicing, how different things will be then. Okay, so why I should learn about communication? Some of you are mechatronics engineers, as some of you are electrical engineers, but perhaps you're more interested in, you know, automotive industry or other industries. So you might be wondering why I'm talking all about communication. Why do I take communications classes? Why would I be interested in this? First of all, we're kind of in the age of smart systems. You know, talking about smart homes, smart cars, smart infrastructure, all of these things need communication to work because they're filled with computers. You look at your average car now, it's over 100 little microprocessors. One of them controls steering, another one controls the gas system, you know, another one controls this other thing. So there are so many computers in these systems that you actually have a communication network on your car, right? The CAN bus is a communication network. It has addresses. You know, it's the whole thing. Actually, a car today, and you see this very easily, of course, with the newer cars with Teslas and so on. It's a computer on wheels, and the software has become more and more important. And if you want a system to be autonomous, it's essential that not only does it work in itself, but it has to be able to collect data from other sources, including from other cars, from the road, maybe look at weather, look at road conditions, look at traffic, all of these things. And if you want the car to actually go by itself, it needs to make smart decisions based on this. So it is very much a communicating computer, right, with a large part of communication in it. And it's very important also, there are criteria that have to be met, both on the computing side and on the communication side. On the computing side, if you press the brakes had better work. If that is a packet going over a network, that packet needs to get from whatever sensor is on the brake to the actual system right quick. Like that can't be delayed by the music you're listening to, which may be on the same bus, right? So this is a communication constraint. In the same way, if there's an accident right in front of you and your autonomous car has to stop, again, the information has to get in a timely manner, be processed, and come to a result. So these aren't just autonomous systems, are embedded systems with strict time delay constraints that have to be met, both on the computing side and on the communication side. Computers and computer networks are vital parts of all systems, automotive, aviation, aerospace. I guess we've done this. Control of system, and then you have a human interface, right? So we're actually the worst part of the system because we're the people, we have a slower processing time than the rest of the system. And so the system has to work with us. There has to be an interface that will allow us to get the information in the best way, right? So that we can understand what's going on. And there's actually a lot of work on that with many areas, especially cars. There's computers, there's going to be software, there's going to be communications, and of course complex communications, spacecrafts, aircrafts, not just or cars, right? Everything has this complex communication networks on it. Communications is in itself a booming industry because of internet, of course, and you have both satellite networks and with the just the increase in the proliferation of low Earth orbit satellites, the small satellite systems. I don't know if you know about these. They have satellites now kind of on the size of a box, right? A cube. and then this thing can take pictures. It's a little cell phone in space, is what it is. And and there's thousands of them collecting data at any point in time, and relaying that information back to Earth. So you can get information on traffic conditions, on, they've tracked murders using this. They find out where the murder is done, and then they follow the cars back, because it was to the source where they came from, to their house, using satellite. So there is, but all of this is possible. You have to communicate with the satellite. And if you consider how many satellites there are currently, that's a whole area. And then, of course, wireless communications on Earth. You have cellular communications just increasing and being used increasingly. And so, all of this is a great industry, like communications for systems that we use in daily life. So anyway, information technology is a critical engineering discipline. So you guys have to know how to work with computers, and you have to know how to work with communication systems, because you will most likely have to use them. Around 2 years ago, like up until 2 years ago, I had a lot of students asking, why do we study communications? Around 2 years ago, students who were working started coming in and going, I can't get my network to work. What is going wrong? So they have, because they're working in factories or in production, and a lot of the devices that are working in there are networked. They're connected to a network. And then if that network doesn't work, it's their job to fix it, because it's not exactly an IT problem, because these things are not computers. They're machines, they're robots, right? They're like production equipment. But they are networked and using some system, usually very similar to the Wi-Fi system you use to connect your laptop to the base station, like your Wi-Fi at home, just with slight differences to make them more robust. So yeah, even the vehicular infrastructure systems, one of the protocols for that is based on Wi-Fi, right? Because we have so many chips, can just change a few things and make it work for an industrial application. It's cheaper than trying to design your whole network communication system from scratch, which is a big deal. So anyway, yeah, you're going to very likely, in whatever job you get into, there will be a network. You will be expected to work to make it work. And if you're in a production environment, in a factory or some other production environment, then that might be a more difficult problem than just getting the network running in your house, right? Okay, so communications applications, broadcasting, digital audio, digital video broadcasting, all of these standards are new. DVB is, there's terrestrial digital video, there's satellite digital video, there's internet digital video standards coming out, because most of us today actually they have this DVB standard. We either use satellite or internet, right? I watch everything on the internet, so there's actually a standard for that too. And like I said, the majority, they didn't have that there, but somewhere, yeah, okay, the majority of network traffic today is for video. I had a graph for that, but I couldn't find it. If I find it, I'll put it up for you, because currently about 70%, like I don't remember exactly, but about 60% of the network traffic pre-COVID, before COVID, was video from Netflix and YouTube, right? So it's just an incredible amount of video being watched. Of course, because we get our information visually. It's so much easier than reading a paper. Even research papers today, I go to their websites and they have a little video explaining the research paper. This has become common for research papers. And it's great, because you can easily understand this person is trying to explain something to you. Really, YouTube is still on the lead? Okay, I got to look that up. Thanks. Yeah, probably. I'm sure Netflix has shrunk because there are so many other providers that are coming in different countries. So Netflix is probably shrinking, but YouTube seems to be, it's maybe TikTok, but yeah, getting up there. But anyway, so yeah, but it's video, right? And the thing is that this may not stop with video. You're having these immersive games. So like Roblox, for instance, my daughter plays Roblox all the time. She's 11. So I don't know if you have younger brothers and sisters or you play Roblox or networked games. So these things are going to probably become more interactive and more network related. Same as, yeah, exactly, right? All the time. So yeah, so the network traffic is driven by a lot of these applications, and it's just increased. The network traffic goes up like this per year, like just like exponential increase. I'll find that data for you. Okay, so digital telephony, is it over? People talk on the telephone, but now with the starting with 4G and then with 5G standards, voice is just another service, right? So it also the voice is packetized also. It goes into the same slots as the video games and the videos and stuff. So that means that voice is like fixed. It's like 3 kilohertz maximum bandwidth. It's a tiny amount of traffic. Video is way more traffic than that. So it's an increasingly smaller part of the total network load. So telephony is there, right? But there are so many other applications that it's just a tiny drop in the bucket of all of the network traffic. And of course, with computer communication networks, there's an issue of resource sharing because there's only so much frequency available. With going to 5G, I'm going to talk about frequencies in a little while. But the way the communication works is that you basically have a channel, and that channel, like imagine like TV channels or radio channels. You change the radio channels on your car radio. So that's a frequency. So every communication is allocated a portion of frequency, just a little part of that frequency just for them, right? So if the thing is who's this going to go to is the question. So governments lease this frequency, and they decide, okay, this area of frequency at 1.2 to 1.5. I'm making the numbers up because I don't know them by heart. But like 1.2 to 1.5 gigahertz will be for cellular communications. And then they ask the companies, okay, how much money are you willing to give me to use this frequency? And then they divide it among the different companies based on, a mechanism. It started out at the beginning, they were using auctions actually to allocate the frequency. I don't know what they do today. It's more of but what happened with the auctions is some people just bought the bandwidth and then tried to just resell it because they didn't have the equipment or anything. So now they have like more of a policing of this and only sell to people who will actually communicate. Right? So anyway, who will actually use the spectrum. So anyway, so it's resources, and then you have to allocate space for people using those walkie-talkies and police networks and fire ambulance networks to talk among each other, and military networks, and there's a whole spectrum of this. See, I should put a graph showing that too. But yeah, you need to share resources, and if there is more than, like with Wi-Fi, if there's more than one group using the same frequency range, then you need to share that frequency among yourselves in some way. So that's the whole thing. How do we share the spectrum? That's a whole range of research. And I'm going to say this is the age of electromagnetics because I'm seeing in many ways that things have gotten so small and so tight, so small in the electronics, which we'll talk about, maybe next week or the week after, and so tight in the spectrum that we're actually looking at electromagnetics to give us more space. For instance, in communications, in 5G, we will be using multiple antennas. Using many antennas, what you can do is instead of broadcasting your signal everywhere all at once, you can kind of focus it in a certain direction, okay? And how do you compute that? Fundamentally using electromagnetics, okay? On a chip, as things are getting smaller and smaller, what you're doing is you have because you can't just think of things as resistances and capacitors anymore. It's just too small. Everything is radiating as if there were tiny antennas, right? So you actually have to use electromagnetic analysis in order to figure how this works. So because our resources are so used up, really, we're using electromagnetics increasingly to calculate things in more detail, so we can get just more throughput out of the same, more bits per second. More users using the network when you're using the same cable or the same frequency. Okay, so computing, mainframe computers, the old days, you're actually moving to distributed computing now. right? With things like blockchain, for instance, is essentially a distributed, secure processing system. But with many applications, you have part of the application running on your computer, part of it running on the telecommunications network, and different parts of it running on different people's computers. So, and then on your computer, there are multiple processors, right? So you have multi-processor systems, and all of those need communication, right? You're computing something that you need to, join it with what the other people are computing in order to send it. And in fact, there are, particularly for sensor networks, or what are sensor networks? Sensor networks are networks of tiny, very small, usually small. They don't consume a lot of energy. They're usually designed to stay in one place and just collect data, right? For instance, looking at air pollution. And things like that, where you just have to, or structural integrity of buildings. You just put them in one place and they collect data from there. And then they collect, but they're multiple places. So they have to put the data together and send it up, right? So those are sensor networks. In those kinds of systems, they also try to do computing and communication at the same time. Can we send it in such a way that when it's on the air, it adds, right? So that this sensor doesn't have to do an extra work. It just sends it at the right time using the right system, and then the other sensor also sends its data, and they collectively add, and at the receiver I find the sum. Things like this, to join computing with communication. Of course, we're also connecting to more and more peripherals, usually using Bluetooth. Maybe there'll be other algorithms, other communication methods coming out. You have smart shoes and smart watches. You have a whole body area network that needs to work, right? And then, of course, you have the application of big data, right? And what do you need for big data? Big data, essentially, you need the information collected from multiple places using sensors or cameras, different independent devices. All this information has to be processed in some way, and then stored somewhere. At least part of it has to be stored somewhere and then processed in some way using statistical inference algorithms, essentially. So all of that together, that the collection of the data, the transmission of the data, the storage and the database access, and then the processing of that using what are fundamentally signal processing techniques. Big data processing is, number one, signal processing, number two, statistics. Right, statistical analysis. So the kind of the merge of the two. So you need to process those, and those systems together make up big data systems. And of course, you have internet services and apps used increasingly. And today, the majority of network data traffic is for internet applications. The majority of network traffic is for video. Internet traffic applications are video. Okay, so anyway, so those are communications applications today. I didn't put in smart devices, which should have been a thing here, right? Maybe I'll just add this for next year, smart devices. Smart devices, cars. What was it called? The fourth generation manufacturing, right? The dark factories that they talk about, right? So you have, it's dark because you don't need light. You don't need light because there's no people in there, right? So the idea there, again, these machines have to communicate among themselves and with the outside. Okay, elements of digital communications. So we've now decided communications is important. Now we're going to look at the elements of digital communication. First of all, these are the physical things you have to do. First of all, analog. The world itself is analog. Sound is analog. Pictures are analog, videos, everything is analog. So you have to, first of all, convert it to digital, right? And this involves two steps, fundamentally, sampling and quantization. Next step, so you went from an analog world to digital bits. Everything's in your computer now. Next step is source coding and compression, because there's so much extra bits, right? If you have a digital camera that has, if you ever had a digital camera, they would have the original RAW format, and then they would have the JPEG format. And the RAW format was usually like at least 10, 100 times bigger than the JPEG format because of this compression. Everything can be made smaller. A simple example, if you look at this slide, right? If you try to save every pixel on the slide, that would be a lot of bits. But you know what a fax machine does? The old-fashioned fax machines. They write down something like this. They go white pixel, and then they go 100. Okay, so that gets you here. And then they go black 1. Okay, and then white 100, black 1. See, that will store a lot, like that's a lot less information than trying to put all this together. Now, if you have an MPEG system, this is what it does. It looks here and it sees a pattern. It says these tiles. And it goes, oh, let me make this a vector. Okay, and then it says, well, all over this, at this location, there is this vector. I'll just send one of these, and then these are also compressed, and then say, repeat that all over the slide, right? So it does things like this. Or you could just store these as ASCII text, right? Store the font, undo. Store the font, store the text. So you don't have to store a picture as a picture. There are many ways to store the picture. The same is true of speech. You can process speech to make it very, very small. And video, if you look at video, because of the way it changes, our eyes are, we want to see the same picture, just change slightly, right, over multiple versions. So what you can do is you can store the first version and then say it moved to the left. And then there was just send, I'm just drawing things. Like this picture, if it was moving, you just send this picture one time, and then you send the direction of motion and say it moved down this much, right? So the TV just draws it a second time, just moved. And there's many more things you can do, like identifying objects which are moving, and then saying where they moved, things like that. Okay, so source coding is this. And then you have information transmission, modulation and detection. To transmit, you have to, put it on a network and so on. We'll talk about that. That's a big thing. Modulation and detection. Okay, modulation. We won't get into this. If you take communications, then I think we'll talk more about modulation. It's too much for this class. You have something called channel coding. And you know how I said with source coding, what do? You have a giant big image. You try to represent it with as few bits as possible. Now, the problem with this is 1 bit error, and you have changed many things in the image, right? Because it was compressed. So what you have to do now is add extra bits. But you add them in a strategic way so that if you have 1 bit of error, you can correct it. Okay, or maybe 5 bits of error, you can correct it. So this is a whole topic, like channel code. I took a whole class on channel coding, right? But the idea is very fundamentally add some extra bits and add them in such a way that they will help you to get the original message, even if one of the bits is wrong when you receive it, right? And then link design, this can go into multiple access control, the different types of physical layer you have, just how you decide who's transmitting in a system. So there's a lot of stuff, again, in here. And then networking. Okay, so you have network architecture. We'll talk about this to begin with. 7-layer network architecture was the original plan before there was the internet. This was the original plan, how we're going to do communications. And then there's packet communications, obviously. How do you packetize things? How big are packets? How do you break them up? And multiple access and LANs, queuing theory, routing, TCP/IP, internet. So these are many. Again, I usually teach a class on wireless networking, and this is fundamentally what we do in the class. We do all of these topics, and like queuing theory is 4 weeks, right? Routing is usually 1 week. So yeah, this is a big topic. Okay, so let me talk about the 7-layer model. It's also known as the OSI model. To start this off, I don't actually have this as a slide, but the ITU, the OSI, and 3GPP are 3 of the main communications, organizations that are used. And the reason we have these is so that the different governments can coordinate among each other, so that they use, initially the idea was, if you have radio, like suppose you have 2 countries next to each other, and one country uses a certain frequency for their radio transmission, And then the country next door uses it for their emergency systems, for their police network. Now, right on the border between the countries, one country's radio transmission is going to interfere with the other country's police network. So that's going to be a problem right there, right? And the second part of this is if you are a manufacturer in any country and you want to sell a radio, right? You want this radio to work in any country that they take it to, preferably, right? So you want there to be a coordination, like you're designing this radio to work in a frequency range, a given frequency range. So you need everyone to agree on this. So this is why they came up with the OSI. I believe it's kind of under the United Nations. Mostly the members are governments and sort of intergovernmental organizations. And they decide what frequency goes where, how you should have a cellular network, all of these things. Now, then they realize that, of course, it's not just governments. The big companies have to be in with this because they're the ones who are going to make the equipment, right? They're going to make the Ethernet cable and the routers and the cell phones. And so they should probably have something to say. They have the development, the research and development staff. So the ITU, I believe, has some sort of non-governmental members in there, consortiums of companies and things like this. And then they kind of became more commercial. They were like, well, you know, governments should give frequencies, should lease the frequencies, but really maybe the companies should have more of a say in how these frequencies are going to be used. What kind of modulation methods, what kind of receivers, transmitters are used. And then there was the 3GPP. The 3GPP came out when 3G communication networks were going to be proposed. I was going to have an extra slide for this, but I'll just tell you briefly what the G stands for. So there's like 3G, 4G, 5G. So the way communication works is communication researchers, professors or in companies, they do research all the time. So they're always coming up with new ideas about communications. But to actually implement this, you need a company. You know, you need Ericsson or whatever, like Motorola or Samsung. I'm coming up with everything, somebody like Xiaomi or Samsung, to actually make your phone. You need them to make your routers, right? For them to become an actual system. And that's not what researchers do. So, but the companies only want to make these if they can sell them. And they need to sell, first of all, they need to sell the base stations to the service providers, which are different companies, right? So Türk Telekom, Avea, all of these companies. So the service providers have to want to buy these things. So for this cell phone to be produced, a 5G cell phone to be produced, everybody has to agree that they're going to produce these and the cell phone companies are going to buy them. And they also have to, be able to depend on the users to buy the cell phones as well. Because otherwise, another service provider can say, oh, I'm not going to use 5G. I'm going to stick with 3G or 4G. And if they're cheaper, people will actually, they won't update their cell phones. They'll just use the old cell phone with the cheap network providers, right? So the other service providers are going to lose money. So there has to be kind of an agreement on what's going to be done as you're moving along. So the 3GPP came up at the time when they were moving on to 3G networks, because there were so many and such different proposals for 3G. There was a CDMA proposal, an OFDM proposal. There was like 7 proposals, and each of them had big companies behind them. There was Motorola was one, IBM was one, Ericsson was one. Like, so there was a lot of arguments during those presentations. But anyway, with the 3GPP, and 3GPP started out with a 3G in the name, but it's also the organization continues, and they're the ones that decide on 4G and 5G. So they hold yearly meetings, and at some point they all kind of decide, okay, everybody's going to make money if we go on to the next generation. So if we change this system in the physical layer, if we change this type of router, if we change our applications are going to change to these. So if we do all of these things, everybody's going to make more money, and the consumer is going to buy this new thing, right? So once they decide that, they will all change the system, and they decide, and they go, yes, now we announce 5G, we'll start. And then they decide on what's in the standard. So there's always some arguments between companies and between countries, because the countries want to support their own companies, right? About what standards are used. For 5G, one of the ones was famous ones was for encoding. For channel coding, the channel coding I'm talking about, currently the most popular, so this one. Currently, the most popular type of channel coding codes are called LDPC codes. They're used for the digital video broadcasting and digital audio broadcasting. So if you have satellite TV, your system does LDPC coding and decoding. They're used in the 4G standards. But the problem is a lot of the decoding algorithms are patented and patented by European and US companies. And China didn't like this. So China their researchers went in, different companies, and they figured out there was another class of codes that can do as well as LDPC codes, and they're polar codes. And they were actually invented by a Turkish professor from Middle Eastern Technical University. And they're not as popular because LDPC was used in actual systems and these were not. So actually the standard today, so China and other countries decided, okay, so this is a good idea, let's put this in the standard so that we can have an alternative to LDPC. So in the 5G standard for encoding, you can use LDPC or you can use polar codes. So yeah, so what I'm trying to say is this is very much about money, about the different companies, about patents and things like this, not really about the technical part. The only time the technical part comes in with this 4G, 5G is when they decide, what new services can we do with this? What can we make with this new systems that we have? Okay, so we have here the 7 application layers, and the thing was the initial systems was a telephone, right? And telephone, you start calling and then you get the other end. And at the beginning, there was just a human operator connecting people, all right? Or there's a computer connecting people. But as the systems become more complicated, it becomes very difficult for one company to produce everything for the communication system and to provide services and to do applications. So they said, well, we're going to have different companies doing this. So let's try to make it standardized so everybody can pick one thing to do. And what's really standardized is these links between these layers. The link from physical to data link to network. So for instance, the goal of the physical layer is to give a perfect channel to the data link layer. The data link layer is supposed to assume there are no errors because the physical layer has taken care of all the errors in the system, right? Now this is a problem. I mean, it works for wired systems, but for wireless systems, unfortunately, these three layers are totally linked together. And here we have what are the layers? Let me tell you. Physical layer, which is actually cables, like it shows here. There is a data link layer, which is Ethernet 802.11, just the encoding, decoding, packetization. Make it into a little packet, send it off. Token, some of these are very old. Token ring is very old. ATM is, I guess, deprecated. Nobody uses it really. Anyway, so there are many different, they may be still used in certain places. But yeah, so these are the ones. So TCP kind of, well, we'll see where it goes. So this is networking layer. And in this layer, so the MAC is like, can I send the packet? Now I'm going to send the packet. Between 2 devices is the MAC. Now with the IP, you have multiple devices and you're deciding which, this device want to communicate to this device, but I can't communicate directly. So where should I send my packet? And then which way will it go next? Which way will it go next? Which way will it go next, right? All of these things. In the transport layer, a lot of the time, this is about when you send a packet on the internet, for instance, sometimes one packet will go one way and another packet will go another way. The next packet will go another way. And the problem is these packets can get out of order. Okay, so part of the role of the transport layer is to put everything in order so that it arrives at the right place at the right time. I mean, the packets are in order so you can decode them, right? And the frames are one after another instead of going back and forth. Sessions are inter-host communications. If you write any programs for instance, like a web browser, you write your own web browser, right? Each of the tabs that you open up ends up being a session. So you'll be working with these 3 layers if you write your own web browser. So yeah, you open up a session. So the first thing you do is open a session with the other computer that has the website that you're trying to get to, right? So that's the session. The presentation is when that computer send you the stuff that's supposed to show up on your computer, right? It's the actual what's supposed to be seen. And in presentation, the application layer, that's when you're typing in the web address and your computer is kind of doing everything to send that information to the presentation layer. Okay, so you can see that the top layers of this, 5, 6, 7, are definitely computer engineering, computer science, computer engineering. The bottom layer, 1 to 2, definitely electrical engineering, right? But everything in between, like 4 and 3, 4, in fact 2, 3, 4, and even 5, both electrical engineers and computer engineers, computer scientists work on. Okay. This is a comparison of the OSI model. So they came up with this model before the internet, right? This is ideally what would happen. But in real life, this is what happens with the TCP/IP. So you can see the data link layer and physical layer are often mixed together. So Ethernet standard contains both the cables and also the packets, the size of the packets, all of these things that are part of that. Again, these are token ring and ATM frame relay. These are old networks. Everybody pretty much uses Ethernet. Wi-Fi 802.11 also does mostly this. Actually, 802.11, I should get a figure of 802.11. It involves everything really all the way here, but they also use TCP/IP. TCP/IP also, so it's the network layer is the internet layer in the TCP/IP model, and the transport layer is up here. So actually TCP, the things that it does, actually partly belong here in the transport layer, but also partly belong in the data link layer, because it does some of the network link-to-link processing type stuff as well. And usually on the internet, you have two choices, TCP and UDP. Oh, there's someone said something. Okay. I told you guys why you're look at slide number, mechatronics engineers. Why should I learn about communications? Because of this, okay? But you guys come in and because you will be working on smart systems, hopefully. Like you're not just making a motor. You're making things that will function inside a home, inside a network. You see, when you look at anyway, I already just go back in the video and listen to the rest of my comments. Okay, so you guys will probably, as mechatronics engineers, you will probably, actually, I'm going to say you'll probably not be working in the physical layer, but realistically speaking, when they tell you, make this thing work, it will include the physical layer. And very often, you know, the cables and where they're supposed to go, or it's Wi-Fi, there's interference from a different source. You have to figure out where the interference is coming from. Yeah, like very often you will have to deal with the physical layer, even though you won't want to, okay? Because it's one of the things that can go fundamentally wrong. The other thing that most mechatronics engineers and anybody who's working on like machines and you know, what's called cyber physical systems, right? Physical systems which are networked to the internet will be working on will often be transport layer and even internet layer, like getting that network, the device to connect to the network and get the right IP, right? DNS problems are very common, right? So yeah, you will probably be involved in every part of this. And also, when you're designing your system, although you won't be designing a new communication system, you're often required to tell your boss, your company, okay, we're building the system. Which communication system should it have? Should it have a cellular communication system? Should I have Wi-Fi and then connect it to the cellular system? And you know, you have to understand how these systems work to figure out. Of course, the cost is important, but if you buy something that's cheap and it doesn't work, that's just a waste of time, right? And so you need to figure out like why things work as they do. What's the difference between these two systems? Why should we have system A and not system B? And to know those things, you really have to know some communications. Okay, so anyway, so TCP/IP is not exactly the same as the OSI model because the top three layers also, the computer scientist layers have merged, right, as well. But you guys like DNS, HTTP, right? You will often have to use these. Okay, so basic elements of digital. So I took these slides actually directly from Eitan Moriani's stuff. because, well, not all of these. I'll tell you when I get to, because he's very good at what we're going to do, which is information theory. Okay. Okay, so this is your communication system. You have source encoding, you have a channel encoder. So you compress, and then you put the bits in to do that. And then you have a modulator, which is going to send you to the frequency and also turn your bits into symbols, which you can transmit. Okay, so basically here, in this, before the source encoder, I converted my data to digital, right? The real world is analog. Sensor data is analog. I have to make it digital to put it in a computer to send it. Modern communication systems are almost exclusively digital. The only, I think, analog system I can think of that's behind is the FM radio. I mean, radio in general. Radio still works in Turkey, but even that will probably change. Yes. Can you zoom a bit? Okay, I'll try. Let me see. I just want to get rid of this and also the top layer. Oh yeah, here we go. Well, that's not much help. Okay. Is a little bit better? This is the best I can do on this screen. I can make it full scale. I will try next week to get like a better screen. Okay. Okay. And I can also make this picture bigger. That might be an idea. Okay, so here we have the basic elements. You have a source encoding, channel encoding, modulation, which is actually the process of making your signal analog again, because the real world is analog. So you have to go to the channel. The channel is the problem, right? This is the unknown. It's completely random, and that's what's going to mess with your system. And then you come out, you have a demodulator, and this thing is very complicated because it has to counteract the effect of the channel. Like even figuring out when you're receiving, when did your signal start, right? Am I receiving a signal or is this just noise? Even doing that is very complicated. So a demodulator, you have a channel decoder and a source decoder. So this is kind of the information theory or computer science look at this system. So this is an example of an actual system that I put in. So DVB standard uses something called MPEG. So this part is, this is what you use for satellite television, right? So this part is the encoding part, the source coding part. Okay, so program 1, program N, multiplexed and synchronized. So these are the different TV channels. They're multiplexed and synchronized. And then you have the channel encoder, which is also known as forward error coding, modulation, conversion and amplification, like you're converting it to different frequency bands. And make it the signal very loud so you can transmit it. This is from the satellite, I guess, the transmission from the satellite. And then, oh, cable or satellite or terrestrial. Okay, so it goes through the channel. This is the channel. And then you have to just convert it back to baseband and amplify again because you lost all of the signal here. Demodulate, again, channel decoder. Again, this uses LDPC codes. And then demultiplexing in order to get the one video audio channel that you're looking for, right? So yeah, an example with MPEG, with the MPEG encoding is actually the source coding here. Okay, like I said, the channel is the most important thing. Every channel degrades your system, even fiber optic cable, even though it's very, very isolated and it can carry the signal for long distances, after a while, it will also distort the signal and you need to amplify. And often adds noise, weakens and distorts the signal. Atmosphere, if you're transmitting wirelessly or just Ethernet maybe, or cable, whatever this is. Okay, entropy, information content of a random variable. So the information, the way communication engineers, the way we see information is like water. It's like electricity. It's actually something which is being transmitted. Now, physically, this may not be the case, but when we do calculations, we come up with, it's kind of mathematically this is the case. Okay, mathematically, you can see it as a form of something you're transmitting, right? And for what is information? Information is really a random variable, right? So you're waiting at the receiver, and you're waiting for a 0 or a 1. and you don't know which is going to arrive, right? So that randomness, when it arrives, it is giving you information, right? So the information is a result, the outcome of random variable. Now, some of you, the electrical engineers, will be taking probability, and you will learn more about this stuff. But for the rest of you, I'm just kind of giving you an introduction. So you have a random experiment. You do something random, and the output you will encode into what's called a random variable. So you have a result. For instance, you measure a voltage. The output voltage is X, right? You don't know what it is before you measure it, right? But once you measure it, you know what it is. It's the voltage is 5 volts or 2 volts, right? So you have some probabilities. The probability that your X is 0 volts is some number. It's 2. It can't be 2. Wait, 0.2. Okay. The probability that your voltage is 5 volts is 0.8, for instance. So your signal is either 0 volts or 5 volts. It's 0 volts with probability 0.2 is 5 volts with probability 0.8. For instance, that would be a random variable. So once you don't know if a 0 or a 1 is arriving, right? So how much information do you get if you're told, okay, this new bit is 0, right? So for instance, will the sun rise today? Suppose this is my experiment. I'm going to wait if the sun will rise today, right? Is it going to rise? Yes. I mean, almost certainly, right? So if I find out the result of this experiment, waiting for the sun to rise today, I will get no information because I already know the sun is going to rise, right? So this random event, even though it's kind of random because you don't exactly know before it happens, but another example, a little bit more random, is you have a burglar alarm on your home. Will the burglar alarm start today? Will there be a burglary today, right? Again, if nothing happens and there's no burglary, then it's not a lot of information. It's something I already expect. But if the alarm starts, that will be a large piece of information, right? That will be completely new, completely random event. It will have high information. Another one, oh yeah, I don't know much about basketball. If you guys like this. Will the Celtics win the NBA championship? Since this is unlikely, revealing yes provides more information. Yeah, just like the burglar alarm. When the burglar alarm goes off, that's a lot of information, very important information. Events that are less likely to contain more information than more likely events. Okay, so this is an information thing. So let's try to give this a number. Like you can measure water, let's measure information. I is the amount of information revealed by the outcome that X is equal to, the burglar coming in, right? The burglar alarm going off, right? So that's your information. Desirable properties of I. First of all, if the probability of X is 1 or 0, so it was certain to happen or certain to not happen, then the amount of information should be 0. And of course, because this is a probability, that it has to be between 0 and 1. And let's say that this information I amount has to be positive. You can't take away information. You can only give information. And if the probability of event X happening is less than the probability of event Y happening, then the information contained in X should be greater than the information contained in Y. If X and Y independent events, assuming that is less than 0.5, I suppose, and if X and Y independent events, then the information should add, right? So the information of, burglar alarm going off this house and a car going past, independent events. So the information is added. And so they came up with this, log base 2, 1 over px. How did they come up with this? Well, a man called Claude Shannon came up with it, basically. He sat down and thought about it, and thought, and somehow he came up with this idea, okay? So information is base 2 logarithm of 1 divided by p of x. Or you could say this is negative logarithm of p of x, okay? And it seems kind of random, but it works really well with everything we expect it to do. And using information theory, we've actually made a lot of predictions about what is possible and what is not possible to the transmission rates possible across certain systems. Okay, a measure of information content of random variable is called entropy. Okay, so entropy is the expected value of the information of X. So basically what I'm saying is you can have 2 events happen with the burglar alarm. the burglar alarm goes off, right? Or it doesn't go off. So on average, every second I'm getting some information, and sometimes it doesn't go off and sometimes it goes off. Okay, so I want to look at the average. On average, how much information does this burglar alarm give me? And this is found by adding the probability that it goes off times the information I get when it goes off, plus the probability it doesn't go off times the information I get when it doesn't go off. That's what this is saying. So for instance, binary experiment. Okay, this is the one. Information, the probability P, the burglar alarm goes off. Probability 1 minus P, it doesn't go off. How much information I have? P is the probability it goes off times the information I get when it goes off, plus 1 minus P, probability it doesn't go off, times the information I get when it doesn't go off. Right? So this is considered the entropy of the random variable x, which is the entropy of my burglar alarm. Okay? And h of x is maximized when p is 1/2. So it's maximum when p is 1/2. So it will decrease when p becomes bigger or smaller. And of course, what this means is I can encode the information that the burglar alarm is giving me using 1 bit. Oh, sorry. I saw bits and I was like, somebody's asking a question about bits. Yeah, okay. Yeah. So this is the entropy of this. So what that means is I can store it using 1 bit memory. I can send it using 1 bit per second, or however often I'm looking at the burglar alarm. Okay, so this actually gives me a limit on how many bits I need to store this information. Now, the application of this is in source coding, okay, where you have a picture, a video, and you're going to look at the information content of the pixels in that video. And whatever that information content is, that's how many bits minimum you need to store that image. Okay, so it gives you a lower bound. Sometimes it also gives you how to find the lower bound. And there is an algorithm we will look at. Okay, so given a random variable m with possible values between 0 and m. So the m possible values. So the information content, the entropy of that x, could be as small as 0. You know, if I'm sure that one of these outcomes, the m possible values, but only one of them really is, like the sun coming up, right? It can come up, it can't come up, but I know it's going to come up, right? So the information content is going to be 0 because I'm certain that this will happen. Or highest information content happens when I am completely unsure. So I could have, you know, event 1, event 2, or event 3 happening, but I don't know which one will happen. So I give them each probability 1/3. With probability 1/3, event 1 happens, probability 1/3, event 2 happens, probability 1/3, event 3 happens. That means that the information content for each of them is the same, log 2m. And so the entropy of the variable is also log base 2 of m. I'm sorry, the information content is negative log 2 of m. And yeah, no, actually, log 2 of m. No. Okay, so this is correct. Suppose we conduct an experiment with m possible outcomes. How many bits are needed to represent the outcome of the experiment? Depends. It's between the average number of bits required to represent the outcome of an experiment is hx, between hx and hx plus 1. Because why is the plus 1? Because you might have if you calculate the entropy and you find 3.5, right? You can't have 3.5 bits, right? You can have 3 bits or 4 bits, and 3 bits is not enough. So you might need 4 bits, right? So it's going to be, but the number of bits required needs to be between these two. Okay, so with source encoding, you're going from the source alphabet. What's the source alphabet? The source alphabet, the simplest way I can say it is if you're looking at the pixels on an image, it's actually the number of gray levels that you have, or the number of, you know, red levels and blue levels and green levels, right? So those are your source alphabets. But you're going to map these to a channel alphabet. Now you can decide what this channel alphabet is. Right, so the source symbols can be letters of the alphabet, ASCII symbols, English dictionary, quantized voice, all of these things. Sorry. And the channel symbols are typically 0s and 1s, right? But it doesn't have to be. You can make these in octal or hexagonal content and so on. And the objectives of source coding are, first of all, unique decodability. We are going to, well, there's 2 types of compression. Okay, one is lossy and one is lossless. when we talk about source coding, we're talking about lossless. In other words, for this image, I have exactly one way to represent it, and there is no ambiguity. If I have this representation, I will get exactly this image. JPEG, for instance, can't guarantee that, actually. JPEG introduces a little bit of noise into your system, so into your image. So some of the pixels will change a little bit, but it will be very close. So sometimes it's okay to have some non-unique decodability, right? And compression. But this type, I'm assuming I might be compressing a file, like a program file. And we're getting past the 1 hour mark, and we've gotten a lot of things done. So yeah, I guess I have enough slides for next week. I was a little overambitious. But next week we'll start with this, and I guess this is, yeah, we'll start with this and we'll talk about physical layer. I'm going to do, next week I'm going to do a continuation of this and do just the Huffman coding. Okay, so because that's easy to do. I'll show you guys how to do that. And then we'll look at kind of physical layer of the transmission. But yeah, any questions, guys? Comments? I'm going to put these slides up on the website, and I'll see you guys next week. Yes, absolutely. I'm going to upload the slides. I'll probably have some example questions or something like that as well. Okay. Okay. See you guys. Bye-bye. Go to your next class. Bye-bye. Take care. Thank you. Bye-bye. Oh, it's great. Yeah. Bye-bye.